Okay, hello, and welcome to my channel. Today, we're gonna talk about the completeness of eigenstates and what measurement postulates. So this would be brief. First, we're gonna take an operator that is Hermitian. So we'll say Q hats. And when you have a Q hat, the eigenfunctions of that operator is gonna form like as I wrote before in the last lesson, it would form something like this. You have psi 1, psi 2, and psi 3, and so on. That would be Q1, Q2, Q3 times psi 1, 2, 3. Right? It would form with these. It would with these eigen functions. It would form a set of sort of basis function that when you take any like an arbitrary wave function that is not weird here, that means it's not like jagged and it decays normally. You can write that wave function in a superposition of these eigenfunctions. So that means that example, you have like a psi of x here. You can write them as a superposition of these eigenfunctions. So you can write these as like alpha 1 psi 1 plus alpha 2 psi 2, so on till like alpha n psi n, and that would be, I'll write it as the sum I from 1 to n of alpha I and psi I. So that is what the completeness of eigenstates states. Okay. And next we would want to take a look at the we want to take a look at this this notation right here. It's kind of weird, but I think it's pretty easy to like pick up. So we would write it as this, and this basically means that it is equal to the integral dx. This guy over here would be the complex conjugate. This is basically the light version of, well, this, the bracket notation. That's even more confusing. So we're just gonna use this here for now. And psi of x, take the same thing over there. This I, so we don't know it yet, so we would take that as j. I equal 1 to n. Take that, and we can sub this part out. That part get you the Kronecker delta, which is delta ij. And once you got that, it would just be the sum that gives you the delta. So it can only be 0 or 1, and you would get just the sum of alpha j. So that is just alpha j. You would just get alpha j. No. Yeah, with the Kronecker delta, these two have to be the same. So this is alpha I. This guy is alpha I, so all that, we can say that the probability here would be equal to the sum of the square. There's another way to write this in a matrix representation. These two have to equal to 1. And this guy can also be written like this. I won't see it now. It's good to know it. This is the identity matrix. This is how I write it. It's a bit weird. Yeah, you won't use this now, but it's good to know it beforehand. And next, we're gonna move on to the measurement thing. So in quantum mechanics, if you measure the expectation value of Q in psi, your possible values are these, from Q1, Q2 to Qn, and the probability is, well, P1 to Pn, right? So after the measurement, if you get something, that something would be your wave function. It's kind of weird to understand, but like after measurement, so like find a good way to write this. Say before measurement, you have your psi of x. Then you use a measurement method to sort of, well, sift it, and you would get something specific. So a probability wave like this, right? Imagine this. You measure it, you would get something specific. So from something like, for example, like this, after measurement is something like this. Yep. And your psi of x becomes an eigenfunction. This is how the wave function collapse. No more probability. You know where it is. So no more wave function. It's just a value now. Yep. And yeah, that's it for today. Goodbye.